This is webhooks, near real-time event processing with guaranteed delivery of HTTP callbacks. I'm Alan Steckley. I'm an engineer at Salesforce. I work on the Marketing Cloud applications and data platform services built on HBase and Hadoop. And
hi, I'm Purna Chandra. I work in CAS Data. I work on the open source CAS Data application platform.
Okay. This is an obligatory safe harbor statement. And, okay, so the basic format of this talk, we will give a brief overview of what the Salesforce Marketing Cloud is for some context, and we'll talk about the webhooks use case and what we're trying to do with it, and then a basic implementation of how we built this on CDAP to be scalable and reliable. And then we'll have time for questions at the end. So what is the Marketing Cloud? So the Marketing Cloud is a part of Salesforce which deals with marketing for businesses to connect with their customers through email, social media, SMS, and other channels. Basically, we send over 1 billion personalized messages per day. And we have hundreds of thousands of business units doing business with us, and there are billions of subscribers under management in our system. So we handle everything from marketing campaigns like daily deal sites or any popular businesses you may have heard of that send marketing to you, or we also handle transactional emails and messages like purchase confirmations, or we have financial notifications like fraud alerts to your bank account, or statement notifications for large financial institutions, or password resets to systems. So we have a lot of different communications that go through our system, and a lot of them have high expectations of deliverability, and some of them are even federally regulated. So what is webhooks? Webhooks is a new system that we're using to basically decrease the latency of delivery of these events around our messaging to our customers. So if they send notifications out, we want them to know about the responses to those notifications, the actions taken around those events, and so forth faster. So say subscribers generate events by engaging with messages, like they click a link, or they open an email, or reply to an SMS message, and we deliver that response to the customer so their systems can respond in near real time to those events happening. So a concrete example use case would be like you make a big purchase from a retailer or some other site, and say it can't be delivered, it bounces for some reason, your email box is full, or it doesn't exist, you typed it in wrong. And so we would immediately notify the retailer that, hey, we couldn't deliver this receipt, and their customer service can either take some action in an automatic fashion on their side, or they can just make it so their customer service is aware when you call in and you complain that, yes, we know it's because of this. And that's important because if you do that, you might respond immediately. If you wait 5 minutes, you're like, where's my email? Where's my email? And you might call in right away. And having that awareness sooner makes our customers look like they know what they're doing. But this can all be distilled into a general problem statement, right? That we're basically taking this stream of near real-time events based on customer-defined actions, and we want to, in this case, guarantee the delivery of these events to our customers' third-party systems. And in this case, we have some primary concerns about what criteria we use to select the platform we use to build this kind of system. We had high data integrity needs. You have commerce, healthcare, finance, messaging. Some of this is government regulated. We have a high expectation of data integrity. We needed horizontal scalability. A large portion of our data is this kind of event data. And we had a short time to market. We have to our customers need to respond to market demands, we need to respond to our customers' demands to deliver these solutions. And we wanted something that we controlled the destiny of, so an open source solution was definitely appealing. So, and then some specific implementation concerns that we had about how our data worked in our systems, we also have to join these events as they're flowing in. So you might have two different data streams coming into the system, and one data stream might depend on the other for it to be kind of completed, so you need to join them. Like a response event when somebody clicks an email might only contain a key, and it might not tell you anything about the customer at all. So it's kind of worthless until you get the corresponding send event, which includes all that detail. But they might arrive at different rates through the system. So we kind of have to wait until these events arrive and assemble them appropriately. Another implementation concern is the idea of deliverability guarantees. So each customer endpoint, we have thousands of customers. They all have different endpoints under their control, which may have different levels of reliability or capability to receive events. So they might need different throttling. They might fail at different rates and need retries. And they might have actually different recency or guarantee expectations. So they might have a TTL around when they care about when messages arrive. Like if you're at a kiosk and it only matters if you get it within that minute, then you might just say throw it away otherwise. So, and we want reporting metrics around all this so we can see that we're meeting our SLAs. So this is a basic diagram of a high-level, very high-level architecture of what we kind of wanted to build. We'd have these events arriving in Kafka from various different producer systems. We'd ingest them somehow, and we'd join these streams as they were flowing in and persist them in some sort of store. And then we would route them based on all these different rules for what customers have subscribed to of their own data and post them to external systems. And this is a very simple, like single-threaded, single-instance business logic implementation that we're going to use for illustration here of what this might look like. So you have some map of routes to event types, and you have some processing method that it receives these events, and then when it does, it looks up whether a route exists, and if it does, it posts it to the endpoint. And then likewise, you might have some sort of similar business logic for the joiner, where you have some map or some collection of these these send events with some sort of join key, and as you get these response events in, you look up to see if you've already received the send event, and then if you have, you join them and you route it to the destination. So how do we make this scale? How do we make this scale and make it reliable? So from the storage standpoint, we can use HBase. There's lots of talks on how to scale your storage out, but how do you scale out the application? How do you manage the consistency of the data in the application? How do you scale out the application stack and manage all the instances of the application? How do you coordinate the movement of data in the applications themselves? And so basically, we went through this exercise. We chose CDAP because it offers a lot of these properties and benefits that we liked, and it did it in a way that was easy to understand and implement. So Poorna is going to walk through an example of taking this implementation that we've discussed earlier and putting it on CDAP and showing how we can scale it.
Hi. So let's see how CDAP helps address the scalability concerns that Alan brought about. So let's look at what CDAP is. CDAP is an open source framework to build and deploy big data applications. It has abstractions to model your data and the processing pipelines. And CDAP provides some framework level guarantees for like exactly once processing, automatic error handling and retries, which helps in bringing about scalability. We'll see how that helps. And all of this is done by having transactions on HBase. And you can write both batch and real-time applications on CDAP. So it's an integrated platform for both. And whatever you build, the applications themselves, they run on the Yarn cluster, and the data itself is stored in HBase. So both of them are kind of scalable. So let's see how we can write scalable application using CDAP. So this is the same example that Alan was talking about, the event joiner example. So you get a response event, you look up a send event, and if you find a send event, you do the join and you do the routing. So the concerns over here was how do you scale the application and how do you scale the data store. So let's see how we can implement this in CDAP with keeping the same structure, but getting scalability out of it. So this is how we would implement the event joiner in CDAP. CDAP has an abstraction called Flowlet where you can write your business logic. So each Flowlet is a class. Here we have this event joiner Flowlet, and each Flowlet will have at least one method that's annotated with an annotation called process input, which I have highlighted. So you can think of a Flowlet as something that reads from an input queue. It reads an event from an input queue, does some processing. So in this case, it reads a response event from the input queue, and it does some processing. And the processing over here involves looking up some data from data store. So to look up the data from data store, CDAP has an abstraction called datasets. So what's the dataset? Here we use something called a send event dataset because we are trying to read send events. And anything that you write in this dataset is written on HBase, and anything that you read from is read from HBase. And this dataset, we'll talk about it in a little more deeper later, but this is the basic concept. So this Flowlet uses a dataset. So it's looking up a send event using a dataset, and if it finds it, then it does the join. And then once it finishes the processing, it writes the processed output onto its output queue. So here, to write to the output queue, use something called as an output emitter. And once you're done, you just put it on the output queue. So finally, a Flowlet is something that reads from an input queue, does some processing, and writes to an output queue. So this is an event joiner Flowlet. Then you can have another Flowlet called event router Flowlet that reads from the output queue of this Flowlet and then does the routing. So once you have built your Flowlets like this, you can easily join them together to form a real-time streaming processor, which we call as a Taigon flow. So here we have a depiction of that. So we have a event joiner Flowlet and we have an event router Flowlet, and both of them read from their input queue and write to their output queue. And the operation that the Flowlet does is wrapped in a transaction. So the transaction starts when you remove the input from an input queue, and it ends when you write it to your output queue. And if something goes wrong in between, the whole transaction gets rolled back and it gets retried. And so this gives you exactly one semantics. And the other thing to note is the HBase, the queues that these read and write are persisted in HBase. So there won't be any data loss, and you can retry and also scale. And once you define your processing logic in terms of Flowlets like this, right, which can be retried and which can scale, now it's very easy to scale the whole thing. The only thing you have to do is increase the number of Flowlet instances and partition the data between them using some kind of a partitioning logic. And each Flowlet instance itself will run in a Yarn container, so you don't need a separate application stack to run your application. And since it runs in a Yarn container, it's also easy to create instances, more and more instances. And the data itself is in HBase, so that also scales. And everything is wrapped in transactions, so you can, the behavior is deterministic. If something goes wrong, it gets retried. And so it's easy to scale. Okay, this is the summary. So CDAP makes the life of a developer easier by taking care of all the overhead involved in writing and managing a distributed application. So the developer is now free to concentrate on the business case that he wants to implement than thinking about writing boilerplate code to manage scaling, manage retries, error handling, or having a separate application stack, or managing data between the instances and things like that. Okay, so I briefly mentioned about data sets and transactions before. So let's take a little bit deeper look at what they are. We already looked at how to write applications. Now the remaining thing is how do data sets look and what are transactions. So data sets itself is just an abstraction to read and write data that CDAP provides. So we call it as a reusable data access pattern. So let's say you want to implement an indexed table. So you already have a table, you want to build a secondary index on it. So you have two tables now. So whatever change you make to the first table, you have to make the corresponding change to the index. And you have to make sure that they are consistent. If not, if one operation succeeds and the other operation fails, then the index is useless. So how do you make it consistent is by wrapping it in a transaction. So data sets give you this ability to build higher level data structures based on HBase tables. So once you wrap this operation in a transaction, either both of them will happen or both of them will not happen. So you have that guarantee. And once you have these abstractions built, you can use them to compose higher level abstractions. Let's say you can use them to compose send event data set or response event data set. It becomes very easy to write higher level abstractions. And once you have a data set, the data set in a distributed mode, when you run your application, the data set writes and reads from HBase. And we also have another mode while developing. You can run the whole application that you have written on your laptop to debug, to test a single step. It's easy to do once you run it on your laptop. So in that mode, the data set automatically writes and reads data from LevelDB. And you can also, we have one other mode where you can write unit tests against your data set and your application itself. So in that case, it runs completely in memory. So once you have this data set, you can run it in different modes. And also, once you have this data set, you can share the same data between both real-time processing and batch processing. For example, you have your data set and you can have flows read from the data set, or you can run a MapReduce job on the data set, or you can also query the data set from Hive. So once you have the data set, you can do a lot of things with it. And Tephra is used by CDAP. Tephra is another open source project that we have, which provides transaction support on HBase. So CDAP uses that. And this is what makes the exactly one semantics possible in CDAP. And the transactions in CDAP are multi-row across tables and across HBase regions. And Tephra uses optimistic concurrency control for transactions. So basically what that means that all the transactions that run concurrently are allowed to run, assuming that none of them will conflict. In a distributed system, it's easy to do that by partitioning your data correctly so that the operations themselves operate on different rows or different pieces of data so that they don't conflict. And so all of them are allowed to run, and when a transaction is about to be committed, a check is made to detect any conflicts it might have with any other recently committed transactions. If there is a conflict, then it gets rolled back. Otherwise, the transaction is committed. So since we do optimistic concurrency control, it leads to a lot of parallelism, and you'll have high level of throughput because of this. Since it does not have locking and you don't block other operations from proceeding. And Tephra is open source, and if you want more information on Tephra, you can go to tephra.io. And not just Tephra, as I mentioned earlier, the whole of CDAP is open source. Feel free to check it out and let us know if you have any questions. We have a mailing list. And we also welcome contributions. And we have use cases today like enterprise cloud applications that are already using CDAP. Yeah. And That's it. Any questions?
So, what is the average queue size? So I assume that once the event is processed, with the queue is made up and the event is deleted.
Mm-hmm.
I think we get it.
Oh,
So
sorry.
What's the average queue size that you see in your production system?
So the question is, what are the average queue sizes?
Yes.
So,
By queues, do you mean the queue between the flowlets?
Yes.
yeah.
Okay, so that is the queues. So what the queues store is the output of one flowlet until the other flowlet consumes. So if everything is happening, if the other flowlet is able to keep up with the input, then your queue sizes will be small, which is probably the ideal state that you want to be in.
So the question was, if the queue size, so someone has to always keep up, and that the queue size is guaranteed to be within certain limit, why HBase is chosen as a persistent store for storing those intermediate units.
No, it doesn't have to be. There is no limit on the queue size itself because it's stored in HBase. You can have as large as queue size as possible, but in a typical production system, you don't want your queues to grow large, right? So you will probably increase the instances of the other flowlet so that it speeds up.
So the question was, why did you choose
HBase?
Why have we chosen
why?
HBase for
Okay.
It is
queues?
not for large.
Okay, for persistence. So that for persistence, mainly for persistence, in this queue case, and for scalability, right?
And they can grow large. So you could
If
have,
something goes wrong, then
or
let's say,
you could have bursty data access patterns where,
So you needed a persistent store, not necessarily.
yeah. So with our data, it's very bursty. So you can have it so, say, with email, right? You don't receive. There's certain times of day and certain days of the year that are busier than others. So we might have a very big spike at 8 in the morning, and then another one at noon, and another one at 6 p.m., and then the rest of the day might be a lot quieter. So to absorb those kinds of hits, they might grow during certain times of the day and then kind of catch back up.
So one of the big requirements of any kind of a distributed application is manageability, right? One of the things that Cloudera did with Cloudera Manager is it lets you manage this huge HBase installation. So if you are going to switch to Cask, you're going to lose that visibility. Your developers would not even understand what's going under the covers. I mean, they should, but they may not. So how would you manage your large distributed applications, suppose if you start to use Cask, or how do you do it in Salesforce?
So they actually have a very good management interface, which we don't go over here at all, but it has various metrics and visibility into the running applications and the ability to manage them. And they have RESTful APIs for doing it programmatically as well. So a lot of our stuff we do today is against the RESTful APIs to do it programmatically, but it is still helpful to be able to pull up a dashboard like in Cloudera Manager style and see these metrics visually. Does that answer your question?
Well, I gotta see it. I wish you had demoed it.
Yeah, they have a booth. I don't know if it's going to be open after this, but I think it's on their screen, and you can see it. Yeah.
If you go to cdap.io, then we have sample screenshots and things like that.
Yeah.
Or you can download the SDK and try, because SDK also has similar dashboards and things available, so you can try it out.
Yeah, you can run it in a standalone mode on a laptop, and it has all the normal capability and user interfaces.
Sounds good.
Can you have composite secondary indexes on the data sets? Like, I want to create an index out of 2 or 3 fields.
Yeah, sure.
Hey,
Yeah, you can have any arbitrary linking now. Now that you have transactions, it makes it simpler to write.
yeah, there's some more complex data sets, like they have the OLAP cube data set that kind of handles the translation of the data into HBase rows for you. So it's not just writing rows, it can actually, you can bundle up the logic of a more complex data
Aggregation and
persistence.
things like that.
Yeah.
Any other questions? All right, thanks a lot.
Sure.
This is the